Hi, Oren. So our applications for this term have actually closed already, but it's great that you're coming to these tech talks to learn a bit more about the team. But if you go to our website, which is more people. So if you go to autonomous.ca, I didn't spell that right, did I? If you go to autonomous.ca, there'll be an application page where you can submit your resume and answer a couple questions. And that's how we'll be doing recruitment for next term.
Okay, sounds lit. Thank you.
Very lit. Awesome, guys. Okay, so welcome to everybody to Autonomous's first tech talk for the fall 20 term. So for those of you who are just joined, I'm Charles. I'm the Autonomous team captain for fall 20. And we're joined here by a lot of members from Autonomous. So this event is a recurring event every other week at this time, so 4:45. And different parts of Autonomous will be presenting, about our autonomy stack and our car. So today, our first presentation will be from our mechanical and electrical divisions on an introduction to our sensors. As a bit of context for those of you who are new, Autonomous, we're a team of approximately 60 to 70 students spread across business, mechanical, electrical, and software. And our goal is to build a level 4 autonomous vehicle for the SAE Auto Drive competition, where we're competing with 8 other teams in North America to achieve full autonomy in sort of like a robotaxi scenario. So we started with a Chevrolet Bolt, just a car that was donated to us, and we're adding the sensors and the software necessary to make it fully autonomous. So now I'm going to hand it off to our presenters. I'll introduce them, I guess. So we have Artandu.
Hi, I'm the mechanical director for the fall 2020 term.
We have Frank.
Hi, I'm Frank. I'm the electrical director for fall 2020.
Gokul.
Hi, I'm Gokul. I'm the manager for the radar driver team for fall 2020.
And Sam.
Hi, I'm Sam. I'm the manager for the sensor interfacing team for fall 2020.
Awesome. So I'll leave it for Frank, I guess, to get started. Thanks, guys.
Thanks, Charles. All right, so welcome to the first WATO Tech Talk, where we'll be talking about sensors. So the reason why we're starting off with this topic is because it's such a fundamental topic for anything autonomous vehicles. If you see a lot of these autonomous vehicle courses, you tend to notice that sensors are kind of like the first topic that you begin with. And the reason why is because a lot of things that you do in autonomous vehicles, such as object tracking, lane detection, and all these other cool topics that we'll cover in future tech talks, they all rely on sensors because sensors allow the car to react to these changes. And essentially, you're allowed to perform all these other cool stuff, such as object tracking and lane detection and everything else that you'll see in future tech talks. So that's kind of like the overview of why we're doing introduction to sensors in the first tech talk. So just to break down the content of this tech talk, we'll be first going over an explanation of each sensor. So you'll get to know the models of each sensor that we have on our vehicle, why that sensor is used, and how those sensors work with the other sensors, and essentially how they work down to the physics of it. And we'll also be going over some pros and cons of each sensor to see how best to use the sensors in different scenarios. And then we'll go in to talk about sensor mounting. So Arhindu will be taking over and talking about how to best optimize your sensor placements and more about the mechanical side of mounting these sensors. And finally, we're going to be having our Q&A. So you can ask any questions regarding the content that we cover in this Tech Talk or anything about autonomous. So if you have questions, leave them at the end for the Q&A, and we'll answer your questions as soon as we can. So here's a high-level overview of the sensors that we have for our autonomous vehicle. At the very front,
Sorry.
At the very front of our car, we have two radars. They're mounted on the front bumper, as you can see in the side view and in the front view. Near the roof of the car, we have 3 cameras in total. The middle one is a special camera that uses a fisheye lens, while the other 2 cameras just use regular lenses for performance things such as object classification. And finally, the sensor that we see in the middle of the roof is the LiDAR. And from this front and side views, you can see that the LiDAR is mounted a bit higher than the other sensors, including the cameras. So Arhindu will definitely talk more about why we have this LiDAR a bit higher, but this is the high-level overview of our sensor configuration. So let's start out with the first sensor, the LiDAR. So what is a LiDAR exactly? It's known as a light detection and ranging. It's essentially a remote sensing method that uses light in the form of pulsed lasers to measure ranges to the Earth. And the LiDAR has terrestrial, airborne, and mobile applications. So how the LiDAR actually works is that inside the LiDAR, there's going to be a rotating mirror where the light beam will bounce off of. So once that light beam hits that rotating mirror, that pulse is going to bounce off surrounding objects and return to the sensor. That sensor is then going to use the time it takes for each pulse to return to the sensor to calculate the distance it travels. Another way that the LiDAR can be commonly configured, could you go back? Yeah, is that you just have everything rotate inside the LiDAR. But for most cases, you generally will have a rotating mirror and you have a light beam that bounces off that rotating mirror, and you'll be able to collect information from your environment. So the reason why we use a LiDAR is because it acts kind of the eyes of our autonomous vehicle. So as the LiDAR system is going to be sending out millions and millions and thousands of lasers every second, an onboard computer can record the laser's reflection point, and you're able to recreate a 3D representation of your environment as shown in the picture on the right. And you can use this 3D representation to determine the vehicle's position with other surrounding objects. So you're able to get a 3D environment, but you're also able to extract key information such as the length, height, width of certain objects. And it really makes it really easy to get a better sense of your object and the environments that your car is going to be in. So the specific model that we use for the LiDAR is the VLP32C LiDAR. The reason why we chose this model is because it has a 360-degree field of view, and has the best vertical resolution compared to the other LiDARs, and there's a great power and temperature efficiency, which really makes it really nice when, makes it easy to maintain. And it has a very high point cloud density, so it's able to contract all this information, and you're really able to get more accuracy from your point cloud. So there are some pros and some cons to the LiDAR. So the pro is that data is going to be collected very quickly, and you're able to retain high accuracy with your data. So this means that you just have a lot of high sample density within your data, and you're able to get key information such as the XYZ coordinates of a certain object and even more information from your environment. It's also capable of collecting data from elevated surfaces and works in bright and dark environments. So if you're driving at night or you're going up a hill, the LiDAR is still able to retain this information rather well. And also, the LiDAR really helps in detecting weird objects. So, there are no geometric distortions when it's collecting this information. So, because it's a light beam, so it's a lot easier to pick up on these weirdly shaped objects, and that's what really makes the LiDAR really powerful. However, there are some cons for the LiDAR. It's very expensive. The certain model that we discovered, like the VOP42C, costs around like $10,000 Canadian. So it's rather expensive. And it's also very ineffective in heavy rain and low-hanging clouds. If you notice, a lot of these autonomous vehicles that you see in public are in California or really nice places with good weather, because the LiDAR is able to excel in those weather conditions. But obviously, if you take it to Canada, the LiDAR is not going to do so well if you have lots of snow and heavy rain. So the reason why that happens is because, one, it definitely is going to get damaged by the rain, snow, etc. And two, when you have light going with water, the water can refract that light. So you're not able to get 100% accuracy as you would in the sunny conditions. And even though that the LiDAR does work in very good bright environments, it's still affected by sun angles and reflection. So if you're going down a city and there's a building, a large glass building, it's a sunny day, it's going to be a bit harder for the LiDAR to really extract that information, as it's going to be harder for it to really get the information, because if there's a lot of reflective surfaces, the light may not bounce back correctly and may not bounce back accurately. So it definitely does get affected by sun angles and reflection. So the next sensor that we're going to cover is the radar, and I'll be handing this over to our radar driver manager, Goku.
Yeah, so first we'll go over sort of a high level of the principles of how a radar operates. Basically, it emits radio waves from a transmitter, and then it measures the echo off of objects of interest, and based on that, we're able to derive useful information like the position and velocity of those objects. For example, to get the velocity from a radar, it's basically calculated by observing the change in frequency from when we emit those waves and when we read them again, basically the reflected waves. So we could tell if an object is moving away if the waves have stretched, so if the frequency of the wave has decreased, and if the object is moving towards us, the waves will have compressed, so the frequency has increased. Basically, this is known as a Doppler effect. And in terms of position, we just use a time delay between transmission and receiving that reflection. Next slide. Yeah, so give a quick overview of our software architecture on the radar team. Basically, it's comprised of 5 ROS nodes, each with a unique responsibility in the pipeline. So for our publisher, it converts the raw radar data into useful ROS messages. And basically, these ROS messages contain information like the timestamp and an array of radar detections, which are basically like a bunch of XYZ points with data like velocity and angle, etc. And then afterwards, the processor node filters that data based on like predefined thresholds, such as signal to noise ratio, velocity, our azimuth angle, which is like our field of view, and a bunch of others like distance, RCS. And afterwards, this goes on to the multi-radar node, which is still under development at the moment, but it's going to be responsible for dropping duplicate points because we have 2 radars working at the same time. So sometimes there are duplicate detections, and in that case, we want to drop one of those. And finally, this the visualizer node will generate point cloud data from those radar messages that we like filtered and received. And this is displayed on a module called RViz, which is part of ROS. So there'll be a demo of that a little later. And yeah, we also have a transform node, which is just used for setting up the coordinate system and the point cloud data based on the physical placement of the radars on the car. So yeah, why do we use radars on autonomous, or why do we want to use radars? They're not actually integrated yet, but the hope is once we have them integrated, they'll compensate for some of the shortcomings of other sensors, like what Frank talked about with the LiDAR. So the radar is good for velocity detection and dynamic objects due to the using the principle of the Doppler effect, like we talked about earlier. And it's consistent in pretty much all weather conditions, and it has a further range than most other sensors. So once this is integrated, it'll give us more data points, and this will help give us more accurate projections for object detection, and ultimately that helps the path planning team make more accurate predictions. So the model that we're using is called the ARS430 from Continental. And we chose this model because it has a long range from 0 to 250 meters, and it can perform a couple of types of scans, the near scan and a far scan. Basically, the near scan has a field of view of plus minus 75 degrees and like a distance of 70 meters. And the far scan has a field of view of plus minus like 9 degrees, and it can measure up to 250 meters away. Yeah, so the video on the right is the point cloud data that we display on the RViz module that I talked about earlier. And basically in the bay, that's basically what's happening. There's a table, we have two radars there, and people will just be walking across, and you see those detections in the video. Yeah, so we don't have to play the whole thing, but basically, yeah, the green detections are from the left radar. The blue one is from the right radar. And yeah, and then there's info at the bottom, basically indicating that something was detected.
All right, so it's time to learn about cameras. Okay, let's get into it. So cameras in autonomous vehicles are used for capturing long-range, high-resolution information. It's literally just a camera taking pictures. So two parallel cameras can assist in developing a 3D mapping. Most of the time, cameras are used for capturing 2D information, so such as lane markings or sign information. However, using multiple cameras can allow for a 3D model of an image that is detected. So just think of it as both your eyes working in tandem to give you something like depth perception or show you the things in front of you. So why we use cameras? So other sensors can be limited in range, so such as LiDARs and radars, and they will tell you your surrounding objects. However, cameras can tell you something coming from a far distance, so the upcoming traffic light or stop sign. And 2D objects need to be captured. So as I was saying before, lane markings and sign information is important, whether the lane marking is a yellow line or a white line, or the sign is yield or stop. These are important distinctions that we have to make. And then distinguishing different objects. So LiDARs and radars will tell you that an object is there. As we saw in the demo just now from the radar, you can see, okay, something is detected there, but we don't actually know what it is. So in the picture on the left, you can see this is kind of just object detection, showing that, okay, the box around this car is saying the car to a certainty of 98.9%, persons here and stuff like that. So if this is just a radar, it would be telling us, yeah, there is something there. I don't know what, but there is something. So those are important distinctions to make. So looking now at the cameras we use, or some models that we use. So one of the lenses here is the Fujinon DF6HA-1B lens. So this lens has good stability. So cars are obviously moving objects, and we can't, just because the car is moving, we can't sacrifice the quality of the image, or else we won't be able to tell what we're actually taking a picture of. So this lens provides good stability when it comes to that, and has a resolution of 1.5 megapixels. And the next lens we use is Fujinon FEA 185 C057 HA-1, if you like me saying letters and numbers, lens. So this has a very wide range of field of view of 185 degrees. So just think about your own eyes, and if you're looking straight ahead and not turning, where does your blind spot start? So probably both your eyes together around like 180 degrees. So this is pretty solid for a field of view for one lens on one camera, and has a resolution of 5 megapixels. So now pros and cons of cameras. So pros, to begin with, cameras are essential for object detection. As we saw in the radar demo, you don't know what is there. You don't know if that's a pedestrian crossing or if it's just a car ahead of you. And you need to know these things. These are important. And that's where cameras come in, as well as lane markings and signs. The way when you're driving your own car, there's a different reaction to a yield sign or a speed change than there is a stop sign. So that's needed. Cameras are customizable with different lenses. So just because you have one camera doesn't mean you're always going to get the same imaging. You can customize that with the lenses. So for example, fisheye lenses give you higher field of view, or like larger field of view. So when you're parking and things like that. And then also they have the highest resolution of all the sensors. You know, when you take a picture, and that's why they're used for object detection, you can know right away what that is. Radar, the demo you saw is just an object, and then even for LiDAR, it's still not the most clear images, and mostly just tell you what your immediate surroundings are. Now, cons for cameras, so relatively poor 3D detection. So this is what was going on before. They're primarily used for 2D information. However, we can use them in tandem with multiple cameras for 3D object detection, but it's not the best. And they're vulnerable to low field visibility issues. So you know yourself, if you're taking a picture with your own phone camera, if you're pointing it directly into the sun, trying to take a picture of somebody, you're not going to get the best image. If it's if it's low light, if it's dark outside or foggy, these are all factors that are going to affect the image quality. And it's reliant on how well the software can process the images. So of course, the car itself does not know what a picture is until you run some model on it to actually detect what object that is. It can't just decide. And that's based off how well the software is written and how good the software is. And the field of view limitations require more cameras. So right now we use 2 cameras on the car for a better field of view. Just think of like your own 2 eyes. If you have only one eye, your visibility is going to be different than having both, or different animals have them around different parts of their head to give them different field of views. So sensor comparisons. So looking at different metrics, so resolution. Cameras have the highest resolution, which is why we use them for object detection and 2D information and image processing. Radars have fairly low resolution, as you can see with our own radars. It's basically just telling you that something is there and where it is located from the demo. And then LiDARs have a higher resolution than radars. However, it's not at the resolution of cameras, and that's why they're not used for object classification. And speed detection. So cameras can take pictures at very high or very fast intervals, or very short intervals, I mean, and then compare the distance between objects, but it's not to a high accuracy, and that's not really why we use cameras. Radars, the speed is measured directly. It's one of the use cases of radars, and that's more accurate than cameras. And then LiDARs, they're inferred based on time delay, which can be affected by different factors. So we usually use radars for that. So cameras' main use case, as talked about before, object detection and classification. radars tracking moving objects, and LiDARs generating 3D environments for the car. And now how they work. So as I was saying before, cameras take a lot of pictures very fast, at very short intervals in between. So basically always telling you what your surroundings are, or what you're directly looking at. The radars, as talked previously by Gokul, they shoot radio waves, and then they measure the speed and position from the objects they hit once it's received. And LiDARs work in a similar way with light being emitted. As the LiDAR spins very fast, it shoots light in all directions and gathers the data when it bounces back. So this is more about the comparison, you can see. So in cameras, you see color, contrast, like resolution, range. Those are the biggest things. Those are the best traits about cameras. And it also tells us that it doesn't work well in darkness, direct sun, glare, as talked about previously. Radar works in mostly any condition and has high range and good speed detection. And this is why we use it for speed detection, one of the primary use cases. And LiDAR is not the best on speed detection. However, 3D reconstruction is what we use them, so 3D modeling. And then right under those little graphs, there are two different images of high resolution radar and LiDAR. So you can tell, and of course, you know what this picture would look like if it was taken by a camera. You can tell why cameras have the best resolution. Yes, LiDARs don't have the worst, and you can tell what your surroundings are. However, even myself, it's not the easiest to just look at that and tell what those objects are. And that's where a camera comes in, and radar, I would not be able to tell what that is. So now IMUs, let's get into it. So IMUs are internal measurement units, and they're used to track vehicle position and orientation. So IMUs come with a combination of different sensors within them. It is one sensor, however, they have multiple inside. So they have three main sensors: accelerometers, gyroscopes, and magnetometers. Not all IMUs have magnetometers. If it's not essential, and you could still have a true IMU without it, all a magnetometer does is add an extra 3 degrees of freedom. So every single one of these sensors provides 3 degrees of freedom, essentially X, Y, Z. So what it is the accelerometer is the movement in the X, Y, and Z axes, telling you how fast you're ascending and descending and how fast you're going in general. The gyroscope tells you pitch, roll, and yaw, not pitch, raw, and yaw. So tells you what angle you're facing, it's just telling you your orientation at the center of the Earth. And then magnetometers are your measured orientation to magnetic north on the X, Y, and Z axes. So this is what tells you which direction you're facing in terms of cardinal directions and which angle you're leaning. So 9 degrees of freedom with all of these, each one providing 3. So as I was saying before, typical IMU has one of each sensor per axis, which is why each one has comes with 3 degrees of freedom. So generally they only have 6 degrees of freedom and 9 if a magnetometer is added. So they work by, the data is reported by the IMU. The data reported by the IMU is fed into a processor, which determines the angular velocity by integrating to find angular position. Then based off the inertial reference frame, we take measurements to run them through an algorithm, so some software we have. And then the acceleration measurements are integrated with respect to time to obtain velocity and position in the car's initial reference frame. And this is how we determine things like how fast we're moving or the position and such. So math is useful. Look at that. So why we use an IMU? So IMUs provide localization data, and they serve as a supplement to GPS positioning systems. This is actually something that is useful for the Year 4 competition, applicable to autonomous, because one of the challenges is we're going under a tunnel. How are we going to drive the car, or how are we going to direct the car? And because we don't have any GPS signal anymore, and that's where the IMU comes in. And so IMUs work in tandem with multiple different sensors. They're not always just on their own, and usually with GPSs. So the IMU we have, as well as the GPS, are both provided by Novatel, just for some background. But So this will be important coming to the next slide where we talk about some of the disadvantages IMUs come with. So IMUs tend to accumulate error because of dead reckoning. And what dead reckoning is small measurement errors that we take at the start of or a point of time will accumulate and lead to drift. And this is essentially like if you're doing a math problem and you're rounding at the very start, and then you get to the end and your answer is off by either a whole number or some decimal points, it's because you're rounding. So same thing or same concept here. It's using previous measurements, although it is supposed to be provided in real time, and using those calculations which skew the actual values. And this can be corrected using by having defined limits, where once we reach a certain point, we have to correct our errors and combine data from sensors such as the GPS or LiDARs or radars. This is why IMUs are used in tandem with GPSs.
So I'm going to start talking about the sensor mounting and the basic design methodology that we go through while mounting the sensors and actually designing enclosures for them. So usually for any given sensor, our design scope can be divided into two broad categories, mounting and enclosure. So the mounting deals with how the camera actually sits on the car's roof rack. So in this picture, you can see that we have a series of aluminum extrusions that are going along the roof of the car, and each sensor sits on it. And that's where the mounting design comes in. And the enclosure design is done to actually essentially provide each sensor the protective cover. So in this picture, you can see there's a arch-shaped shell, and these are actually covering the two side cameras in the car. So in design requirements for mounting, one of the main ones is stability, and a lot of it deals with vibration resistance. So we want to make sure that when the car is traveling, the sensors don't vibrate and the mounting is as stable as possible, because not only does that induce a risk of the sensor quite literally falling off the car, but it also will hinder the sensor's ability to take accurate measurements. Furthermore, we also want the mounting design to be as simple as possible. So in the case that we want to unmount a sensor for some reason, we want the design to be as simple as possible so that can be done as quickly as possible without any hassle. For the enclosure, we want it to be durable because we want it to be able to deal with the elements of nature. So for example, for our case, a lot of it, since we're in Canada, it would be snow. It'd be snow and rain. It'd also be dust, and we want to make sure that the enclosure can deal with it. Apart from that, it has to provide appropriate insulation. So even if it's durable, we need to make sure that the enclosure actually does its job and not let any of these elements of nature affect the actual sensor itself. So the design verification for the sensor mounting is done through various methods. The two most common ones are finite element analysis simulation and hand calculations. Usually these are done in conjunction. So we use hand calculations to see what we should expect and see what the design should behave like. And we use the simulation to actually verify that what we're expecting is what's going to happen. So while there are various different kinds of FEA simulations out there, the one that we use most commonly for sensor mounting design verification is modal simulation. So as you can see on the right, there's a picture of the LiDAR mount, and that's the example that I'll be going through today as well to illustrate the process of the simulation. And in modal simulation, the basic principle is various different modes of vibrations are evaluated independently to verify if any of them could cause failure during the design and the implementation. So in modal simulation, there are four major steps. The first one being defining the materials. So that's just taking all the parts and saying what material they are, because based on the material properties, they will have different degrees of susceptibility to different forces. The next step is to generate a mesh. So that's dividing the entire system into very small elements. The third step is defining the number of modes. So that's the matter of just seeing how many different kinds of vibrations do we want to evaluate for failure. And the last one is actually evaluating the results ourselves based on what the simulation spits out. So in mesh generation, it's, as I mentioned before, it's essentially done to divide the structure into very, very small pieces. And this, what the simulation does is it analyzes each element on its own, and the final result is a superposition of all the finite elements and finite elements that are generated by the mesh. So just to give a brief background of vibration mode, a mode of vibration is simply a unique manner of vibration that the system can experience. For example, one mode of vibration could be a beam going up and down, while another mode could be a beam going left and right. And each mode is caused by a unique combination of forces and conditions. And because of that, some modes are more probable than the others. And it's up to us to determine which modes are the most probable and to evaluate them accordingly. Additionally, each mode has a natural frequency associated with it. The natural frequency is the frequency at which the vibration occurs for that mode. And the entire goal is to see that or to make sure that our design avoids resonance at this frequency, because if there's and what that means is the frequency of the frequency that for example the car is traveling at should not be close to the natural frequency, because that's where resonance occurs and that's where failure is most probable. So in the LiDAR simulation that we did, we chose to define 15 modes, and as you can see in the table on the right, we have the simulation spit out all the 15 modes and their natural frequencies. And due to the low frequencies of modes 1 to 9, they can be safely ignored. And modes 10 to 15 then need to be evaluated individually. And based on literature, the vibration of a car roof is approximately 45 hertz. And since we are looking at a sensor that's sitting on the car's roof, that's the frequency that we need to look at and compare the natural frequencies with. So if you just look at the table, we can see that while none of the frequencies come close to 45 hertz, the closest one is mode 15, and we need to evaluate modes 15, 14, and 13, especially critically, to make sure that resonance they won't result in resonance. So now I'm just going to walk through each of modes 10 to 15, and then go through a simple evaluation of each mode. So yeah, the mode anim. So this is mode 10. Oh, sorry. Yeah. Give me a second. Sorry about that. Yep. So as you can see in this mode, what the simulation is basically saying is the LiDAR will kind of rotate along the XY plane, or the horizontal, or the XZ plane in this case. So I'm going to reference this coordinate system here. So essentially rotating about the Y-axis on the XZ plane. And we can see in the table that the frequency is 13.91 hertz. So based on the literature value, this will not cause resonance, but at the same time, we know that this is not very probable, because at the side of these two beams are two long extrusions that are running across the roof of the car, and due to that design, this mode of vibration is not probable in the first place. So this mode can be safely ignored. So then this is mode 11. And as you can see, this is kind of just rocking, and then it's vibrating around the x-axis this time. And then again, this is not very probable, because that would quite literally mean the roof rack is going up and down, and that's a very improbable case. Regardless, we can see that the frequency is low, so this mode can also be safely ignored. So then this would be mode 12. And this one is a very similar mode of vibration, except this time it's rotating along the z-axis. Once again, not very probable, so we can safely ignore it. Now this one is a more probable mode of vibration, because this could occur due to one of the bolts kind of just kind of coming off or becoming loose, causing these horizontal structures to starting to rotate and bend and vibrate. And this is mode 13, and this has a vibration of a natural frequency of approximately 20 hertz. So while this is a probable mode of vibration, when we compare it to our frequency of 45 hertz, we can see that it won't cause resonance. So this mode can also, so then this design passes that mode as well. And mode 14, this one, while it's still somewhat probable, where the bolts come out, it's again still very improbable. And even then, from the frequency table, we know that there's going to be no resonance, so we can also ignore this mode. And lastly, mode 15. This one, once again, extremely improbable, where it's kind of just, it looks like the LiDAR is walking. And even though this mode had the highest natural frequency, it's still, we can safely ignore it because this mode is very improbable as well. So therefore, based on that analysis of these 15 modes, we can safely say that this design passes the FEA verification, and then it won't cause any issues, at least from a vibration perspective. And yeah, if you guys have any questions regarding the entire presentation, feel free to ask us now.
Hi, this is Ben. A great presentation. I had a question about the last part where you talked about, what do you call it? Resonance? What happens when there's resonance?
So when there's resonance, essentially, resonance essentially means two waves they superimpose each other, and then because they have the same frequency, and if they're in phase with each other, that would cause the effects to amplify or double, and double assuming they have the same amplitude, but then usually it means it's amplified, and that's the worst case scenario.
I see. And this will cause vibration, which would
Yeah,
disturb the sensor data.
Yeah.
Okay, makes sense.
Hey, it's Charles. I have a question as well. Again, great presentation. I really enjoyed it. So yeah, for the vibration modeling, how do you ensure that your model is going to accurately reflect how the roof rack behaves in real life? Like, surely the specific bolts or the torque values that you use for your bolts will affect the behavior.
Yeah. So part of it is just making sure that the pre-processed values that we use, for example, the system that we analyze and the design variables that we put in are as close to reality as possible. But also, we also need to make that's why hand calculations are so important, where used in conjunction with simulation, because oftentimes simulation makes assumptions and those assumptions don't hold true in real life. So it's usually bad practice to look at the numbers from the simulation itself. We just look at the behavior, and the numbers are actually used, the numbers of the hand calculations are used more. And it's just a matter of making sure that a simulation is more realistic as possible. For example, we used 15 modes in the simulation. To make the simulation more realistic, could have easily gone to 30. That would have just meant you'd require more computation power and time. And so the trade-off is that the more accurate we try to make the simulation, the longer time it requires, and the more system power it requires as well. So oftentimes we use the simulation in conjunction with hand calculations to verify it numerically and also look at it visually to make sure that the design will work during operation.
Awesome.
Hi, this is Ben again. Another question. How did you guys generate the test scenarios? You mentioned there are 15 modes. What does a mode mean?
So a mode is as a mode is simply just like one of the manners of like a way the thing could vibrate. So like like for example mode 15, if this mode were to occur, it would vibrate like this, or if you look at mode 14, it would vibrate like that. the generation of the modes is done by the simulation software itself. So in this case, it's ANSYS. And yeah, it's just, so the ANSYS just look, so the first 6 modes, they're always by default, and those are called rigid body modes. And you tend to have the lowest frequencies because they're the one, they assume that the system is completely fixed. But then, or sorry, the system is completely free. And the mode we just so for, like so in this it doesn't show it here, but then if we were to go to the solution tab, you can select how many modes you want to identify, and the software simply chooses. So if let's say I chose 20 modes, it'll choose the 20 most probable modes of vibration based on all the system values that I've already put into it.
Very cool. Just to clarify the visualization here, that's
Yeah.
an exaggeration, right? The amplitude.
Yeah, that's definitely an exaggeration. So
Okay.
you can see it here where it's you can't see it clearly from the picture, but then if you were to zoom in, you could see this, and then like the highest it goes to is 0.52657, and that red, when we looked at it, there wasn't anything in the spectrum. It was usually here, and where it's very low, usually in this range, where it ranges from 6.05 times 10 to the power -8 to 0.12 meters.
Oh, sorry. What does that? What are those numbers? Is that?
That's the total deformation. So that's actually how much it deforms by. So deformation is essentially like a measure of how much it changes shape.
I see. And
Yeah.
what are the units for these numbers?
This one
Is
is
it
in
deformation?
meters.
I see.
Yeah,
Cool. Very interesting. Thanks for explaining.
no worries.
Hi, Michael here. Can you guys hear me?
Yeah.
Yeah,
Yep.
so great presentation. It was really interesting. I had another question about this ANSYS software as well.
Yeah.
So as a user of ANSYS, when you design a mode, do
Yeah.
you pick like, I guess like the forces and the combination of those forces to get the animation that you want that we're seeing? And then does ANSYS kind of like spit out as output the natural frequency that corresponds to those forces?
Yeah. So you can specify any additional forces that are there, but then also usually if you specify the contacts, like these gussets, the ANSYS will itself calculate those forces because they usually all forces already associated with them, and then if you want to add additional forces in there, you could, and then that will also be taken into account when ANSYS spits out these modes.
Okay, yeah, cool, thanks.
Hi, this is Jacob.
Right.
I was wondering if you guys could talk about maybe like your signal processing stack, or like I think you mentioned that you're building this off of ROS. It sounded like the multi-radar is like in development right now. Maybe you could talk about how that's going, what your plan is for that. Just speak to that a little bit.
Sure. So yeah, we are using ROS as our framework for the sensors, and we actually are using ROS for a lot of other things. So in terms of the multi-radar, that's in development just because we had some issues encountering with, getting duplicate points, but then we found out that, it was inevitable that we had duplicate points just because we have those two radars that are close together. They're just going to generate noise with each other. So right now, like the radar team is going to be working on is object tracking. So we're going to be figuring out how to cluster our point cloud data and send that over to our perception team to use for object tracking.
Yeah, a big project we have is basically sensor fusion. So we have all these different sensors between the cameras, LiDARs, and radars. But the path planning group, like when you're driving a car, you don't want to know, oh, this data is from the radar, oh, this data is from the LiDAR. You want it all to be in one unified package, in one unified frame, so that you can actually make decisions in a simplified way. So yeah, so Frank was talking about like sending stuff to our object tracker, and that's going to be something that we probably talk about at our next tech talk in 2 weeks about our object tracking and perception stacks. But it'll be that's where our sensor fusion happens, where we get information from all 3 of our sensors, so our cameras, LiDARs, and radars, and we turn those all into unified bounding boxes with a classification label.
So then the multi-radar step, this is going to be like prior to sending this off to, like,
yes,
you're just going to sort of discard one of these duplicates earlier in the pipeline before you get to that.
Yep. So you always have like a high-level fusion. In this case, so yeah, for the radars, we'll have high-level fusion between our 2 radars, and then clustering, as Frank was mentioning. And you do this for all of your sensors. So if you have multiple LiDARs, you'll first, fuse your LiDAR data before fusing with other data. And, we have multiple cameras, so of course we fuse our camera data first.
Right. Cool. Thanks.
No problem.
This is Ben again. Regarding sensor fusion, is there a need for us to do time synchronization between the sensors? And if so, how do we do it? Do we do it now?
Yeah, so we definitely do need to do time synchronization. If you think about it, right, like you want to have the most up-to-date data from your radar and from your LiDAR. So the way this works is that whenever you get when our drivers for our sensors, which are written in ROS, the messages that they send will have a timestamp associated with when they made the detection. So our radar might be detected at like 2 minutes, like some arbitrary timestamp. And then if our LiDAR is detected at 2.5 minutes, we can take those messages and use a package in ROS that does timestamp correlation to kind of fuse messages within a certain error tolerance. So it'll group messages from your radar and your LiDAR by timestamp. And, of course, if something doesn't come in from the radar, you'll just proceed with one LiDAR detection instead.
Makes sense. And we assume that the system clocks are in sync between the different components.
Yes, yeah. I think everything's running on our one computer, so I think everything should be using the same clock.
I see. Right, makes sense.
Hi, can you hear me?
Yep.
Oh yeah, I just wanted to ask, could you talk a little more about your 2D and 3D object detection networks? And just a question, how do you deploy these really large networks on device, in the car itself? You must have some sort of accelerator chip, right?
Yeah, so we'll be talking about this a lot more in our next tech talk, where we actually talk about our perception stack, so our 2D and 3D object detection with our object tracking. But as a brief overview, we have an interesting problem at Autonomous in that Intel is our sponsor, so we can't use a GPU, and that's their rule for the competition. We're allowed to use FPGAs for acceleration, but that was too difficult, so we're not. As a result, all of our models run on CPU, and we have a very beefy CPU. So using Intel's OpenVINO package, we can do some CPU acceleration, but it definitely limits the complexity model that we have. So a big goal for our object detection methods is speed.
Right. Thanks.
Yeah, tune in next week or in 2 weeks when we talk about object detection.
Sure. Thanks. I will.
Awesome. Okay. Any last questions? Feel free to ask questions about Autonomous as well, or whatever. It doesn't need to be specifically about the presentation.
Yeah, I have a quick question. Well, hopefully quick. So I came a little late to this presentation, unfortunately, but so sorry if I missed it. But can you expand more on what ROS is and how it's important to WATO?
Sure, yeah. So ROS is a it's called the Robot Operating System, and it is a message synchronization service that runs on top of Ubuntu. And what this does is this is actually a good diagram here, but ROS is structured in terms of a series of nodes, which are processes, and these are individual programs that we run on the car. For example, our traffic light detection node will be an individual process, but we need to communicate in real time between these different processes. So that's where ROS comes in, and they're kind of like a inter-process communication service. You'll send a message from node A, and node B can subscribe to the topic that node A is publishing to, and then run a callback function that will run some function whenever it receives a message. And that's the main process communication and synchronization that we use.
Okay, thanks. I'll look more into it. It seems like a pretty big topic, so.
Yeah, basically any research autonomous vehicle group uses ROS. Once you get to actually running cars on the street and like Waymo or Uber or something like that, you probably need to build something a bit more complex so to ensure safety compliance. But ROS is definitely the standard for research.
This is Ben again. I had a question about the two cameras that we have. Have we ever considered doing 3D, I guess, detection using both of those cameras? So to simulate, emulate, to mimic a stereo camera setup.
Yeah, so we probably looked at it, but it's quite difficult because if you want to do that kind of thing, you need to run your model twice on both cameras, right? It requires double the processing power. And with our limited computation power, it's not really worth it, since our LiDAR data gives very accurate 3D information. So we could, of course, probably make it better by doing some 3D estimation of the camera as well. But I think from our investigations, it was not worth actually doing 3D reconstruction using only cameras.
I see, makes sense.
Hi, you mentioned before earlier in the presentation that FPGAs was too hard. Do you mind explaining exactly what that means? Like how you're going to use FPGAs as part of the stack, like the autonomous stack for WATO?
So FPGAs we were encouraged to use FPGAs by Intel to accelerate our models. So you can program the FPGA to run the model very efficiently. I wasn't directly involved in this effort, but from what I remember, it was basically we blew up a couple FPGAs because we didn't use them properly, and then it was very difficult to actually have them work successfully and integrate into our pipeline. So we ended up giving up on them.
Oh,
I know a bunch of other teams also had troubles with their FPGAs. So teams like U of T were able to use their FPGA successfully.
interesting. So when you transition to the GPUs, like you mentioned earlier, I think GPU stands for, is it graphical processing units or something?
Yep.
Or do you mind because I just don't really understand what they actually do or how you use them. So I just want to have a better picture.
This is like machine learning, but so a machine learning model, what it basically is a bunch of linear algebra calculations, and you're multiplying matrices together, like a crap ton of these matrices, a lot, and through this problem, you're able to basically estimate parameters using some fancy math. But the main time sink is doing this matrix multiplication. a bit more background, like, so you would use these neural networks for like detecting objects in a camera. You can estimate the parameter for what the object is and where the object is. So a GPU is very fast at doing these matrix multiplication calculations, which is why people use them for machine learning. An FPGA can be used to approximate this process as well. But then a CPU is just not really designed for that kind of very linear, kind of just pure math calculations. It's more about like optimized for doing different branching tasks. For example, running your OS, you're going to have a bunch of different things that might happen, a big tree of operations.
And so that means that the perception team would be working mostly in that area, like with the machine learning and using the GPUs and stuff.
Yeah. So again, we're not actually allowed to use GPUs, but they'll be training models for their CPUs and etc. Yep.
That makes sense. Thank you.
No, just another question about this FPGA thing. Did you guys like build your own FPGA, or is this like something that you can like buy off the shelf with like Amazon or Alibaba or something?
Yeah, Intel provided us with a FPGA. I'm not sure what model.
Oh, cool. I'll look into it. Looks interesting.
Well, awesome. Okay. Thanks everybody for coming. That was a great first talk. Thanks for all the questions, and thanks again to the presenters for the great presentation. I hope that you guys will join me and join the rest of Autonomous in 2 weeks at the same time, where we're going to talk about perception. So thank you again for coming.
Well, good presentation. See you guys.
Bye, Ben.
See ya. Happy Thanksgiving.
Yep, you too.
True
Forgot
Thanksgiving.
about that.
Adios.